Hi everyone, we're talking about Euler's method. This is very similar to Newton's method that we've already done, except this is with differential equations. Okay, now I mentioned in the slope field video that there's some differential equations that we cannot solve. Hey, this is an example of one. Hey, if it's not separable right now, we don't know how to solve it. A lot of differential equations just aren't solvable, but we can get an estimate, and that's what Euler's method does for us. Okay, so we're given a differential equation, okay, and an initial condition. Okay, so what we want to do is estimate the value of the original function at 4.2. Okay, that's what we want to do. So here's what I know. I know that y prime is x plus y. Okay, another way of writing this is that f of x comma y equals x plus y. All right, so just like f of x, except since we have two variables, it's f of x and y. Okay, that's what I know. Okay, something else that they told me was my initial condition. So what that means is that f of x sub 0 and y sub 0, okay, which is just, 4 and negative 1. So that's the point that they gave me. Okay, this is x naught, this is y naught. All right, so x sub 0, y sub 0, 4 and negative 1. Okay, and if I plug these into my equation, where f is my derivative, I get 3. Okay, so that's what I know so far. Okay, the value of my function at my initial condition is 3, meaning the slope. Okay, the slope of y is 3. Okay, now using Euler's method, I want to start at x equals 4, which is what I just did, and with two steps of equal size, approximate 4.2. Okay, so if I'm going from 4 to 4.2 with two steps of equal size, that means each step is going to be 0.1. I'm going to call that h. So each step is going to be 0.1. All right, now here's the process. We have to go one step at a time. So first, I'm going to approximate f of 4.1. Okay. I'm going to approximate f of 4.1. Now, in order to do that, I'm going to have to name some variables and such. Okay, so f of 4.1 is y sub 1. Okay, that just means that's the y value after one step. Okay, this is the y value after 0 steps, is negative 1. The y value after one step is going to be the estimate to f of 4.1. Okay, we're trying to get to f of 4.2. Okay, the formula for this is initial plus step size times my function value or my derivative, however you want to think about it. All right, so here's my derivative evaluated at my initial condition. Okay, another way that you might see this written is just f sub 0. Okay, you might see it written that way, you might see it written this way. There's a bunch of different ways you can write this out. Okay, from here we just plug in numbers. So y sub 0 is negative 1. H is 0.1. All right, and then f naught, or f of x sub 0, y sub 0 is 3. All right, and if you do the math, you get negative 0.7. Okay, so again, this is an approximation to y sub 1, okay, or f of 4.1. I want f of 4.2. Okay, that's what I want to get to, but can't get there yet. Okay, so I just went through one step and I found that x sub 1 and y sub 1 is the point 4.1 and negative 0.7. Okay, so here's my next coordinate. Okay, my original coordinate was 4, negative 1. Okay, my next coordinate is 4.1 and then negative 0.7. That's what I found. Okay, now using this, I'm going to find f of x sub 1 and y sub 1. Okay, so just like I did up here, okay, same process. I just have to do it again. So f of x sub 1 and y sub 1 is essentially f of 4.1 negative 0.7. Don't get all these f's confused. Okay, right now I'm plugging into my derivative. That gets me 4.1 minus 0.7, which is 3.4. Okay. now I can move on to approximating f of 4.2, which I'm going to call y sub 2. Okay, so we go up a step. This is recursive, so it builds on it. So now instead of using y sub 0, I'm going to use y sub 1. H is always constant, and this time it's going to be f of x sub 1 and y sub 1. Okay, that's why we had to find that again. All right, so y sub 1 is negative 0.7. My step size is constant, and then f of x sub 1, y sub 1, we found was 3.4. Right? You do the math, you get negative 0.36, and that is my estimate. Okay, so again, I couldn't actually solve this. Okay, I couldn't even get a general equation. Nonetheless, a specific answer to this using my initial condition, but I could get an estimate near my initial condition. Right, and that's what Euler's method does. That's it for these notes. See you all later.